Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The title of my talk's Automated Termination Analysis of Programs Using Term Rewriting. So there's probably two questions in your head now. The first one is, why termination analysis? And I mean, the other one is term rewriting. Why term rewriting? And I mean, I'm going to answer both these questions in a minute, starting with why termination analysis. And well, this is joint work with my colleagues from Aachen and my former colleague here from Aachen, who has now moved to Austria, and two groups of logic programmers in Belgium and in the Netherlands. So why termination analysis? Well, first, it's a theoretically interesting problem. It's very fundamental. Turing already had this as the first undecidable problem in his 1936 paper. But I mean, that's not all of the reasons why we are interested in it. It's also useful. So if you want to have correctness of your software, you need to prove that it does compute the right thing. But normally you do this by assuming that it also terminates. And so termination is an integral part of verification. And also it's a requirement to some more analysis and program transformations. And of course, it's an interesting property on its own to know that a certain algorithm terminates. And you can, for example, reduce liveness problems to termination, or even verify device drivers so that when they acquire a lock at some time, you can make sure that they will also release this lock. So there's this very nice Scientific American article sent in the Terminator. It's about Byron Cook's tool. I don't think probably you've seen that before. So now our approach is to reduce the termination of programs to the termination of term rewriting, because, well, that's going to be later why we want to do this. But what is term rewriting? Well, term rewriting is a very basic principle of computation. A term rewrite system you can just imagine as a set of equations over terms, and these are built from uninterpreted function symbols and variables. And then rewriting with these terms is just replacing instances of left-hand sides by right-hand sides. And if we want to represent a function like, let's say, the Ackermann function here, which is a non-primitive recursive, famous function, well, there you have, in our notation, 0 and successor here for piano integers, natural numbers, and ACK for the Ackermann function, and P here as a predecessor function, just to make it a little bit more interesting. And if we want to compute the Ackermann of 1 and 0 now, well, we have to match it with some rule. And here, this second rule here works. It matches by instantiating x by 1. And then we can replace it by the right-hand side. And here again, we have to instantiate this x here by 1. Well, and then we can apply the rule for the P. The predecessor of the successor of 0 is 0. And now, again, for this rule, we need to match it with some of the Ackermann rules. And we do this with the first Ackermann rule. And we can then rewrite this to 2. So Ackermann of 1 and 0 is 2. And I don't want to show this for Ackermann of 4, 4 or something. That's going to be huge. So we could spend all our life on that and it wouldn't be finished. So how can you imagine what this principle of computation is doing? Well, a term you can imagine as describing the state of the computation, and the state transitions correspond to the rewriting steps that you take. And well, there's been a lot of interest from the beginning in termination analysis because of one of the most basic properties of these rewrite systems. And I think it started in 1967 with someone presenting some ad hoc ordering, and the real nice first parametric solution was in 1970 by Donald Knuth and Peter Bendix with the KBO, Knuth-Bendix ordering. And then in the following, let's say, 15 years, people invented better and different orderings to show termination. But the idea was always to show that the rewrite relation is embedded in some well-founded ordering. Well, and this is not very powerful, unfortunately. So from the beginning of the 80s about, people have sought for new techniques that can go beyond these simple orderings, these simple ranking functions, if you want. And especially in 1997, the technique of dependency pairs was discovered. And this is very nice for automation. And I can quote from a last report on the termination competition. There they said it was a disruptive change when this was introduced, and people started thinking about really automating all this work that had been done. And tool building started in around 2000, and in 2003 at some workshop on termination, there was already a session comparing 6 of these tools, and people found this very interesting. There was a lot of interest from the community. So in the following years, there was an international termination competition each year where those tools could compete against each other. So how does this work? Well, there's as an input terminate system, or also a Prolog program, and nowadays even Haskell 98 programs. And the output is yes, no, or maybe, where, well, yes is green and means yes, it's terminating, definitely, we've proven it. No is more like we found a counterexample, and this is a real counterexample. So there is some input for which the program does not terminate. And maybe is, well, it's undecidable, and we can prove it using our techniques, but we didn't find a counterexample. So for each of these examples in the competition, you have like 1 to 5 minutes of time, depending on who organizes the competition and the other details. And there's a big problem set, the termination problem database, containing like 2,500 terminate systems and lots of logic and functional programs. And well, for term writing, the first 3 tools for the last 4 years are displayed here in this table. And fortunately, this is our tool, so that's nice. But why is this the reason? So what is better about our tool than about the other tools? Well, it's not that we have some single silver bullet technology that can do what they can't, but it's more like we have a big modular toolbox, and there are over 150 different techniques. I mean, some of them are polynomial interpretations or size change principle ranking functions or lexicographic path ordering, dependency pairs, but there's many other things that you can do using automata or other ideas. And well, in the input, there's a term write system. On the output, you have some human-readable proof or some machine-readable proof that later then maybe can be checked by some automated checker. And the idea is that you can combine all of these modular techniques. If you have a given term write system, you can just apply them each other, and they will transform and reduce and simplify these problems. And you build a proof tree, and in the end, you get some nice HTML output or whatever you prefer. So that's not the only tool. I mean, even if we did win the competitions, there's a lot of other tools from other groups. And you can say that it's a well-developed field. And there's a lot of active research still going on. So the latest conferences on rewriting techniques, it was the most important topic for papers. I mean, most submissions and most accepted papers. And also at other conferences about automated deduction or verification. There's a lot of research there. We have powerful techniques and tools, but well, let's be honest. Who programs in term writing here? I mean, okay, we have this. Ah, you do. That's great. In Boogie, I mean, there's these axioms, and these are like term writing. I mean, there's some places where you can use that. I mean, I can show you a very short demo of our tool. And wow, there should be a terminal somewhere. Ah, it's down there. Okay, so it's developed by a whole bunch of people, mostly students. And well, you can load some input. Let's say we take this Ackermann function, but in a very simple fashion, just without the predecessor function. Can you actually read this? Yeah. Maybe the contrast is a bit too high. Yeah. So maybe this is a little bit, no, this is not better, right? Ah. Okay, so what happens here is it builds a proof tree, and here it says it has found a termination proof with the lexicographic path order. So that was a very easy example, and this could have been done at the beginning of the 80s. But if you just add in this predecessor function, and that's the version that we've seen during the talk, then already it doesn't work with these simple orderings. Actually, you can prove that it doesn't work with any of them. And you need to apply the dependency pairs technique or some other thing that goes beyond just the simple orderings. And well, then it will apply lots of techniques, and you have a whole proof tree here of techniques being applied, most of them just simplifying the problem slightly. Okay, and now there are some applications, of course. For example, at Ericsson, they use Erlang, a functional programming language that they use on their telecom switches, and you can specify protocols like leader election or something like that in Erlang, and then you can translate them automatically to MuseRL, which is a specification language, and then this is very close to term rewriting. So this term rewrite system is basically just a translation of the specification of this leader election protocol. It has a few hundred lines of definitions and looks very nice. And well, we can show termination of this. And what's nice about this is that at this step here, it says it found 33 strongly connected components in this problem, and they are all able to be analyzed separately. And so we have many modular proofs here to handle this problem. And well, how long does this take? I mean, it takes about 33 times as long as the Ackermann example, just because the complexity of each of the modular problems is not much bigger. Okay. Well, back to the talk. So the application in practice is a problem right now still, because term writing is not that popular. So what do people use? People use programming languages. And I mean, they use imperative languages. And most notably, there's work on linear ranking functions. And building on this, together with some abstraction refinement idea, is the Terminator tool by Cook and Podelsky and Andrei Rybolchenko. And well, this is nice. It works on the full C language. Well, it's not totally automated, but close to. And it's actually used to find bugs in Microsoft device drivers. Well, it's not well suited, on the other hand, for your own data structure. So it's not very good if you're like doing something nasty on the heap, or if you define your own methods that you use in conditions of loops or something. Then this is also not very powerful yet. And there's many techniques that exist for term rewriting, and they're all very basic, and they do lots of different things, not just compute ranking functions. And you can't use them here because at the moment it's a standalone thing. You just find a ranking function or you give up. Well, for functional languages, it looks a bit different. So there is a lot of work on that. On doing that for first-order strict languages, or finding some type system which is probably not very nice to write a type checker for, which ensures termination. Then some work on lazy termination in a rewriting setting, and on lazy termination in a very small subset of Haskell. But well, these are all not working on some real functional language, and they don't use any fancy techniques, just they usually find some polynomial interpretation or ranking function, some simple measure, and then they are done. For logic languages, this looks a bit different again. So there we have two different approaches. The direct approach works directly on the level of logic programs, and it's quite well developed. So people have had this problem that you give a query and it doesn't terminate, or you don't know if it terminates because it runs for a long time. They have had this for a long time, and this is really a fundamental problem in Prolog. And so they have developed techniques and tools for this. And well, they are not bad. They do a quite good job and can prove termination of many examples where it would be tedious to do it as a human. So that's nice. They really work on Prolog. But still, they are standalone methods, and they are only based on finding linear norms, basically. And so we're again back to linear ranking functions. Well, the second school of thought, that is the transformational approach. So a lot of people have been inventing transformations, I think like 10 different transformations during the 90s. And one of these transformations is also implemented in a tool. And this is quite nice. It makes available all those techniques from term rewriting. And this tool is quite competitive with the direct tools. So For some examples, it's better. For some examples, the others are better. But the problem with these transformations, at least the ones that we've had up so far, is that they're either restricted in their application. So you have the restriction of well-moded logic programs where basically you can simulate the unification in the logic program by matching. Or if that's not the case, they're not so restricted, well then they are somehow encoding and term rewriting the unification operations and other things. And you can always give from one Turing complete language to another one some translation, but doing some analysis on that is totally impossible, I would say. Let's say at least it's hard. Well, and now if you want to apply term rewrite techniques to programming languages to somehow improve the state of the art, to be able to prove more things terminating, then you have two basic approaches. The one is doing it directly on the level, porting some of the ideas of the techniques that people have had for term rewriting to the level of the programming language. Or you can take a transformational approach and take whatever termination problem you want to show. So let's say some procedure in some C# program or whatever, and transform this into a term rewrite system that doesn't have to be equivalent and computing the same thing, but which has to have the same termination behavior. And then you can show termination of this term rewrite system and thereby termination of the original program. So we've been working on this for the last, let's say, 2.5 years, and we've so far contributed in 3 ways. The first is that we ported some techniques from term writing to logic programming. Then we have a better transformation for logic programs where we remove the restriction to well-moded logic programs, but we can apply it to any. And well, then we also have a transformation approach for full Haskell 98, including type classes and records and whatever you don't want to use in Haskell. Okay, so yeah. Well, yeah, actually, let's say this we have done in our group, this transformational method. And then some people from the logic programming community, most notably Danny De Schreye, he saw this and was very intrigued and said, oh, let's try to port these techniques to the logic programming domain and see how it works if we apply them directly. I mean, so we thought this would probably be better. The difference between these approaches? Yeah, I'm going to show both of these approaches shortly, and if you have questions, then I'm happy to answer them. No, it's complete in that way that we can take any Haskell 98 program and get some term rewriting problem from that, but no, it's not complete. I mean, when we are complete, we can also have non-termination analysis, and that works for many things, but that's, I mean, we handle lambda abstractions, we handle higher order, we handle lazy termination. Oh, actually, we may do a little trick which I will explain in this part of the talk, and there you will see that how we handle them. That we, in the end, we don't need to handle higher order really, but we will have a transformation that gets rid of this before. Okay. Yeah.
Throughout, you're assuming that there is no hint whatsoever from the programmer in the form of a loop variant, or
so far, yes. I mean, with imperative programs, right now we're here discussing with both Boogie and Clouseau people, and there we are very happy to have some invariants or some generated information that we could use. But so far for logic programs and functional programs, we don't assume any annotations. Okay, I'll start with a direct method for logic programs. So first, to see how we translate dependency pairs to logic programs, you need to understand dependency pairs. Luckily, it's very easy. So we have this term rewrite system up there. And the idea with dependency pairs is that you just look at which function can call which function. And here, we have definitions for P and for ACK. So whenever you have on the right-hand side ACK or P, well, then you add a new rule saying that you can go from this left-hand side, so from ACK x0 here to P of x, or you can go from x0 to the whole site. Well, you do this also for this other rule where we have defined symbols here, ek and ek. So you add this one and this pair. And, well, this looks like not something very useful, but the good thing is by going into the right-hand sides up here, you get rid of the monotonicity restrictions for the orderings that you can use. And also you gain the possibility to have some more modular approach. And now what happens for a logic program when we do the same thing here with the Ackermann function? Now this is just like encoding the function by saying this is the input, and well, here the output then is x. And so the predecessor of x plus 1 is x, and the Ackermann of 0 and x is s of x, and so on. And now the approach for doing this for a logic program is the same, but you need a triple. Well, why is this the case? Well, first here for this Ackermann to p call, it's okay. You can just do it like up there with the term writing. But if you go from this Ackermann here to this Ackermann, well, you have to know what happens to the y. And the y is instantiated by calling pxy. So you need this as kind of a guard or condition on this recursive call. Otherwise, you would be pretty weak. Well, if we do the same for this rule here and add these two more pairs, the second one again with the guard here. Now, what we were interested in with dependency pairs, or now with dependency triples, is always how these recursive calls can follow each other. Well, in this case, we will just make a very easy criteria here. We'll just look at the recursive call of one pair, of one triple, and then at the head of another triple. And, well, if they unify, then we assume that Prolog can go from one call to the other. Of course, this can be done better, and actually it's undecidable in general, and there are better approximations than what we are doing here. If they are not unifiable, it's impossible to go from this recursive call to this one in the next step.
So is the interim atoms, the red part, is that just the list of predicates?
That's just the list of atoms in the body before we get to the recursive atom, yes. And, well, then we build a graph from this where the nodes are just our triples. And the edges, well, we have a directed edge from 1 to 3, let's say, if the recursive call 3 can follow after the recursive call 1. And now if we have any infinite derivation in the logic program, then this must somehow correspond to an infinite sequence of recursive calls. And this infinite sequence can, of course, only be in some strongly connected component, or at least an infinite suffix of this. So that means that all the parts that are not in some strongly connected component can be removed. And so we get rid of the first of these triples. So now we have computed the triples. We have computed this graph and deleted the first triple. And now we still need to do something about the remaining problem. And here the idea is to find some measure, some ranking function if you want, to show that we're somehow not doing this infinitely often. And, well, one approach would be to say we interpret these parts of the triples by some measure. And, well, for these, all the heads to the recursive calls, we have to be at least greater or equal. And for these two here, we can assume these guards they have to hold. And we use some R as an abstraction. And here we will just say R contains all Ackermann atoms. And, well, for the predecessor, we have a very coarse approximation saying the first argument is bigger than the second argument. And if we do that, and then define a measure which says we measure Ackermann by the first argument, well, why do we do this? We have here x plus 1 and here x. So it's a good idea to measure with the first argument. And here we have s of x and s of x, so it at least doesn't get smaller. And here we have x against y, but we know, well, that p of x, y has to be in this relation, and that means with our abstraction here that t1 is greater than t2 and that is x is greater than y. Well, then we get exactly these constraints if we interpret these atoms. And now we see that for the first and for the third one, we even have a strict decrease here. And these strictly decreasing triples can now be deleted. And our problem becomes much easier. So now we go further in our procedure, see, okay, we deleted something. Let's recompute the graph. Now there's only one strongly connected component left, quite trivial one. And now we're going to look for a ranking function for this one. And this time we're going to use, again, a measure, but this will measure the second argument of Ackermann. And by this we see, okay, we have y plus 1 here and y there. And this is a strict decrease, and we can remove this. Well, and how do we find this? Yeah, these measures we find by setting up some symbolic form of these measures. So that, let's say we take linear ones, then it would be some constant plus some other constant times t1 plus.
Components, you kind of lots of components that guess a strategy and then
Yeah.
try to work.
Yeah, basically we set up an abstract measure, and then we search for the coefficients using.
But setting up this measure is kind of a guess, right?
Yeah, that's a guess. Yeah, sure. I mean, what are you going to use? Are you going to use quadratic or to the power of 4, or are you going to use exponential functions? Sure.
So, in terms of ordinals, if you get an ordinal for the first component,
Yes.
an ordinal for the second,
Right. You could view this as kind of.
it's a sum, weighted sum.
Yeah, that would probably work directly. So I mean, oh,
But it's, so to say, ordinal sum, so you give the most weights to the first one.
right. I mean, you could also use a lexicographic combination of orderings or a lexicographic path ordering, and this would be able to do this directly. I mean, without doing it in 2 steps.
But there's no suppose that the second component was sort of helpful basis for the, there's no feedback.
Or you can actually here use this first component again if you want. I mean, also in the first part. So these are totally unrelated, these orderings. And that's also a difference to what was there in the logic programming world before. I'm not sure this answers your question, but maybe we can take this offline. Okay. So now we removed the last triple. The graph is empty, and we're happy having shown termination. So we have adopted 2 of the most popular techniques from term rewriting, just 2 of, I would say, dozens or hundreds. And this has been implemented with our partners from Leuven. And it's now the most powerful tool for direct termination analysis of logic programs. And you can see this at the competition of last year. It won the 2nd prize. Well, we're going to look at these question marks in the next part of the talk. And the future work might be to adapt further techniques if you really want to do that. Well, okay, the second part is going to be about transformational approach to logic programs. And here the idea is just that we add this Prolog here as another input language to our system. And then we try to add some modular techniques which will allow the other techniques to be used. Here we have a small example using list concatenation, where lists are represented by empty list nil and the list constructor cons. And it's quite basic. And the classical approach is that you divide this up by some input and some output arguments. So for append, this could be like you take the first 2 arguments to be the inputs, and the third argument is the concatenation. And if you do that, then you can, for each fact, add some p in to p out rule. So you say, if you have to prove app of nil x's, well, then you start computing with app in nil x's. And then immediately, because it's a fact, you can say, oh, I've proven app of this nil x's. And, you just put the input arguments for the in and the output arguments for the out version. And for the more interesting clauses where you have some atoms in the body, you make some kind of conditional translation. So here, if you want to prove P, well then try to prove Q with the input arguments. And if you can do that with these bindings for the output arguments, then you can get these bindings for the output arguments of P. And if we apply this to the append, well, this looks just the same. So if we have some const x's, ys, well, then first append x's and ys. The result is zs, and then, well, the result of the total computation is const x zs. So in a way, we're treating logic programs like functional programs here, and we're assuming some direction of input and output. And the intuition is that whenever we can prove p in of the input arguments goes to p out of the whenever we can prove p of the input and output arguments, then, well, the in of the input arguments goes to the out of the output arguments and has the right bindings. So now we can have a nice theorem that says when this TRS terminates, then also the logic program does. This is nice, but unfortunately this only holds for well-moded programs. Why is this the case? Well, for non-well-moded programs, we would get extra variables on the right-hand side. So let's say only the first argument is an input argument. Then we have here a free variable on the right-hand side. You could instantiate this by anything. Especially, you could also instantiate it by app-in of nil. And then you would have app-in of nil goes to app-out of app-in nil, and app-in nil again can be evaluated. And there you are with your infinite computation. Well, we thought this is kind of stupid. So we improved this by just saying we don't make this distinction of input and output, but we just take all the arguments. I mean, if you can prove app nil, well, if you want to prove app nil is x's, you have to evaluate it to app out nil x's, and the same for the other rule. And now the idea is that you don't have this distinction anymore, and everything is fine. Well, almost. The thing is that you have to have infinite terms for this to be sound. And this is because you have to simulate the unification of the logic program by matching. And with this well-modedness in the classical approach, this was not a problem because you would always make sure by well-modedness that the input arguments would be ground terms, so they would not contain any variables. And then unification of some term with a ground term is the same as matching. But here, we don't have this restriction at all. And this means that to simulate unification by matching, we have to put all of the substitutions in the unification chain at the beginning. So the input term can become infinite. But that's not a big problem because it's very easy to extend dependency pairs and afterwards to be able to use all the techniques we have in our tool. And that's actually what we did. So there are 296 examples which we tested this on. And well, the first 3 tools up there are the tools that have existed before our work. This is a transformational tool. These are the best direct tools that had. This is the new best direct tool, which I showed you in the previous contribution. And well, this new transformation is way better, especially if you see that there are only 244 at most terminating examples. Some of them we don't know. So for this benchmark collection, which is from many papers over the last 20 decades of termination research and logic programming, we are pretty much maxed out. And it's always better. It's not only that we're more powerful in the sum, but there's only one example where another tool can prove something which we can't. And this is because we constructed this example as a counterexample to the completeness of our method and submitted it to this database. But there was no pre-existing example in this database where our tool fails when another tool succeeds. Well, that's not really true. I mean, all the tools require that you give some kind of query specification, and you can do this using modes normally. And so in the competition, it's that you give modes, but only for the initial query. And then the tool has to do a mode analysis on its own. And the kind of analysis that we do is actually more powerful than just a simple groundness analysis. But what we do is we can also express things like the list is finite, but contains variables or something like that. So that's yeah. I mean, we got to do this at some point. Yes. Oh, cuts and negation as failure and so on, which can be expressed by cuts. We're actually just now working on this. So we have an idea which is pretty close to the Haskell work, which I will show you in a minute, using the same idea. And that's very difficult, but it looks like it's going to work out. So yeah, here we have again the Ackermann program, this time for logic program, and we specify the first arguments to be ground on the queries, so kind of moded to be input, input, output. But this is just for demonstrating the translation here. And now if we look at the proof, well, we have the Prolog program here, then we have a transformation to the terminate system. And well, this is just the same idea. So you have here ACK in of something goes to ACK out of the same thing. So that's this new transformation. And what is it doing afterwards? Well, afterwards, somehow this keyboard doesn't. Now it works. So it should expand all of them. Well, afterwards it uses dependency pairs and the dependency graph and then some other techniques. And here, I think this is the main step where it finds some nice ordering. It's yeah, in this case it's lexicographic path ordering with this precedence on the function symbols given down here. And of course, we can handle slightly more interesting things. Let's say we have this merge sort program, which is a bit nasty because the split thing only terminates if the inputs are non-empty. And I mean, this the analysis has to somehow find out. But well, there's no other tool that can do this proof. But for our tool, it's pretty easy. And that's because we have this modular approach. And down here, these steps with rewriting and narrowing, these are all basically simplification steps. And by this simplification steps, they also do some kind of case analysis. We can easily find out that split is only going to be used in this way, and that therefore it's terminating. Okay, so what should we learn from this? That it's good to use terminate techniques for logic programs. And well, in the results of the competition, the most powerful tool is now our tool, and that's using this transformational approach. So I'm not sure about us investing much more time into translating more terminate techniques to the Prolog level. Possible future work here would be to combine direct and transformational approaches, and this would be to handle things like cuts and so on, because the cuts, they require some kind of analysis on the level of the logic program already. And if we have done this analysis, then from there we would take a transformational approach, because for showing the termination or the absence of infinite computation, we feel that the term writing level is more suited. So we've seen two approaches for logic programs yet. Now we go to our approach for functional programs. Well, it is the idea of just adding another input language to our system. So I will have to extend these slides when we have more languages. And well, you could think that it's pretty easy to do, because Haskell, like logic programs, it works on terms and does simple replacing of terms in some expressions. But there are a few challenges, and these are not very minor. So the first thing is the lazy evaluation strategy. In term writing, you can either prove strict evaluation innermost, or you can prove all reductions, but there's no way to specify exactly Haskell reduction strategy. Well, then in Haskell, you order your equations, and depending on how you order them, the program has a different meaning and different termination behavior. And in TRSs, we are non-deterministic, and we can just choose any of the rules for the given term as long as the rule matches. Then Haskell has polymorphic types. I mean, luckily they're not full system F, but still that's pretty nasty, and it's more importantly important for the termination proof. So it can be that without the types, the program does not terminate. Actually, there are programs which do not perform any computation. They just are written like f of x is x, but if you give the right type class definitions, then the type of this value is always decreased, and it terminates. And we can handle this example. Well, in Haskell programs also there are functions because of lazy termination that do not terminate on their own. So I mean it's pretty useless to say, oh, give me this Haskell program, I'll show that all of the functions terminate. Well, there may be something like from calculating an infinite list, and then you can show termination. And last but not least, we have a higher order language here. And well, that is a problem because there are some approaches for higher order term rewriting and termination analysis of that, but these are not very powerful, not very well developed, and very complicated, so we didn't feel that we would want to apply these.
Just on the typing front.
Yeah?
Was it type classes that gave you the problem? In other words, is it type classes or is it polymorphism?
Well, type classes...
Suppose you didn't have type classes. Would this bullet still be on your slide?
Yes, probably. I mean, I'm not sure. Let me see. Yeah, I mean, with type classes it's easy. You can have the equals, and if you don't overload this the right way, then this doesn't work. But for, I'm not sure. Probably there's no problem then.
My suspicion is not.
Yes, I mean, if the program is, we assume that it's been type checked and correctly typed. So, I mean, anyway, it will make the from the practical point of view, it will make the analysis more powerful because we can also look at the types and use this to see that some computation is not possible. Whereas without the types, we might, I don't know, maybe if we instantiate in our reductions in the term rewrite system, the variables by terms which are not type correct. This is something we can do because we have no types in the term rewrite system. Then this might pose a problem. I'm not sure. I will think about this. So if we take this from example, where take just takes a finite prefix of a given length of a list, and from compute the infinite list of numbers starting from m. Well, then if we evaluate this one step, we get m and then from of sm, and then the list containing m and s of m, and so on. This is non-terminating, clearly. But if we now take, let's say 1 of from m, well, then this terminates because we first evaluate this from, we get some element, we take it, and then we have take 0 of anything is just the empty list. And thus we have a list containing only one element. So we have to somehow do this also in our analysis to somehow see that we can show termination for terms of the form take something from something. So in general, in these start terms, a variable can be instantiated by any terminating Haskell expression. So you can put in anything that on its own terminates again. Otherwise, it's pretty useless because then it's just an analysis if this argument is going to be evaluated or not. And well, a naive approach would be to just take the Haskell equations, turn them into term writing using some desugaring, and we'd be happy. But of course, if we do this for the from rule, we get from of x goes to cons x from of sx, and well, that's not terminating. So our approach is that we do a symbolic evaluation of our start term and try to build some finite graph which can represent all the runs of the program. And then we transform this graph into a term rewriting problem. So we start with the initial start term, take u from m up here. And now we have some rules how to add children in this graph. And the first one is the case analysis called case. And well, there we of course still know the type, so we can say u is either 0 or n plus 1. And now the semantics of this is if these two terminate, then also this term up here should terminate. I mean, that's the semantics we want to have for this termination graph. Now there's the evaluation rule called eval, and with this we can evaluate this to nil. And well, here we can first evaluate the from and then the take one step. And then we need to get rid of this constructor here because we want to know what's happening with the arguments. So we just strip off the constructor and look at the arguments on their own. Well, this terminates because we assume that all the variables are instantiated by terminating Haskell expressions. But what about this term? Well, I could now look, well, the n here what is it going to be? Is it going to be 0 or is it going to be S of something? And then I could do this case analysis. Then I could evaluate the branches, and then I could do a parameter split, and then I could, case analysis, and so on. And this I can do forever, because even if this program, the start term is terminating, it can have an arbitrary derivation length. So what we do is we have an instantiation rule saying, well, let's look at this term and this term. This is more general. So this is an instantiation, and so we add an edge here back to that term. And then we also have to look at the instantiation here and see, okay, the U is instantiated by n, so we have to show termination of n, and the m is instantiated by S of m, we have to show termination of S of m. Well, this is easy using the parameter split. Then we just get m here. So now we have a nice termination graph that's finite. And we can always find such a graph where we can not expand any further. And the reason is that if things get too bad, we can always take x, y, and from z or something as new nodes in the graph, and then we can instantiate to these nodes. And this is, of course, an over-approximation, and we will probably not be able to show termination anymore. But we can always close this graph in that way if it gets out of hand. And the only question that we now should be asking is, well, if we say, if these two are terminating, then this is terminating. Great, then we know this is terminating. If these are, well, this is terminating because this is terminating. Great. This is terminating because this is terminating, because this is terminating, because these two are terminating, because these two are terminating, and this one is terminating. That's not good. I mean, we're somehow chasing our tail. So what we need to do is we need to find an argument why we can't do this infinitely often. So why the program can't go through this loop infinitely often. And this looks a lot like the things that we do in our dependency graphs. And there's one more thing that we have to handle before, that is the higher order. But let's just say, instead of writing x applied to y, we just write app of xy. And so we have a first order applicative system there. We transform all the lambdas away by giving them names before we build this graph anyway. So this way we get rid of the higher order. This is one way. Actually, in our implementation, we don't need this because we can prove that what we will do later to these loops doesn't require us to use higher order terms, but that we can always have a first order term just looking at those components that change. And now, if we prove termination of all the terms here, well, that's nice. We can do this by finding some TRS which corresponds here to this loop and show that this loop can't be infinite. But it's even better to take this directly to the level of dependency pairs, because we already have this loop structure here. So we don't care for what happens down here and this here. We are already on a modular level, and also on this level we still know about type classes and other nasty things. But if we put this into a term-rewrite system, then maybe it will find another loop somewhere, which is not really there with Haskell evaluation, but which could be there in the term-rewrite system. So what we want to do is just show the termination for each of the strongly connected components. Well, here there's only one strongly connected component, and now for each path here, which goes down from a place where such an instantiation edge comes in, down to where such an instantiation edge leaves. So basically, for all the loops that we have here, we generate a dependency pair. And well, this is here our only path that we have. And note that we have here a substitution of replacing u by s of n. And this means that always when we take this loop, then here we don't have u, but we already have s of something. And of course, we want to make use of that fact. So what we create as a dependency pair is this term here, where we instantiate the u by s of n. And the right-hand side, well, that's just the term down here. Now, if we can show that it's not possible to go infinitely often from this recursive call to itself and so on, then we have shown that this loop here is well-founded. And then also that our argument of if these two arguments, if these two children here terminate, then this terminates, and well, if this terminates, and so on, is also well-founded and therefore sound. well, as you can probably imagine, proving the termination of this thing up here is pretty easy. So what we're actually doing also with the logic programs is that we're not just taking the program, but also some kind of query or start term. And then here we are plugging it into this graph, and then we're translating the graph to dependency pairs. So let's look at how this works. Oh, come on. So here we have definitions for take and for from. For simplicity, the take works with natural numbers, the first argument like in the talk. You can also do this with integers. And while we are working on the built-in lists, and now if we give it the start term, take u from wrong kind of keyboard. Okay. Well, then we can probably I changed something. Okay, I have to re-enter the term. Now I can execute the termination analyzer, and it finds a proof. And if we look at what happens here, well, it first does some reductions on the Haskell program. In this case, it doesn't do much, just replaces the underscore because we don't handle this in the graph. And then it builds the termination graph. And as you can see, this looks pretty much like what I showed you on my slides. Only that here, with the S of M, we're not taking the extra step of stripping the S because we say it's a constructor term, and we already know that this terminates. Now, this is transformed into a dependency pair problem, where here we have a decrease on the first argument. And, well, u0 plus 1 is bigger than u0. We can definitely find a ranking function which will do that. And actually, what we're using here is the size change principle, which is what Lee Jones and Ben Amram introduced for functional programs. But of course, we can also do more interesting things. So let's say here we have a plus defined on the natural numbers, and we have a sum function which takes all the nets in a list and sums them up. And well, we also have a higher order version of that, taking some function which takes a list of nat and and returns a nat, and then we take a list and return a nat. And well, this is just what you would use in the fixed point semantics of this psum function. Then we have a version of the isum here, which works on real integers, so on the ones that Haskell uses. And then we have the corresponding higher order function. And last but not least, we have this nice fix function, which says fix of f is f of fix of f. So what we are going to do is we're going to look at a number of proofs. So we are interested in what psum does and what isum does first. Well, first we can prove termination of both of them, and then it does two different analyses for the two different start terms. The first one is the psum with the with the self-defined natural numbers, and this is just like we expect. There's a case analysis up here for the empty list or the non-empty list, and well, once we get rid here of the plus by saying we have to also look at the termination of plus, then we have an instance here going back, and because vx3 was instantiated by vx31, we get a decrease here. And for plus, the same thing happens. We also have one loop here, one case analysis, and one instantiation. Well, and what happens for the one working on integers? Well, there we have to supply axioms for what the built-in operation plus does. So the thing here for the isum itself, that looks exactly the same structure. But, oh, where did it go? Oh, I lost it. Okay, there it is. But here, the plus, well, that's the prim plus int, and we gave axioms for that. And now it has to show that with these axioms it works. And there are cases for when you have to really do a subtraction or an addition. And this is still pretty small for an example working on integers, so they can get pretty nasty. Okay. Yeah, that's in Ben Rinnes in Speyside, Scotland. Very nice. Went there before SAS and Lobster. Okay. Haskell PNG it should be called. There we go. Yeah, it's so this is just the take from with real integers. And well, you can probably not see anything because it looks gray and this projector is really bad. It's true. Okay. Now, I mean, I have to. You can see. Yeah, now you can see in the gray areas. So I can see both areas. But yeah, there's. It's pretty big and pretty nasty. And as a last thing, I would like to.
But, I mean,
yes.
Just, being internally, but it just doesn't work, right?
It just works. Yeah. I mean.
Is it much slower?
No. It's just. I would say it's about linear. It doesn't add a lot of.
Because I think it's really important because no one likes to program in piano or number.
No, not really. So let's do fix fi sum. So we are now using the higher order variant here, and we are applying a fix on it. And well, this should compute the same as isum does. And probably again change something in the program, which it tells me I should. Yeah, this is something in the user interface fi sum. Okay. So I can execute this now. And well, this also takes only fractions of a second. And then we get this nice graph. And as you can see, actually it looks quite the same. I mean, we have the plus here, and there's a big deal of plus things. The only thing that's different is here that up here we have this evaluation of fix ones. But then nothing else happens. I mean, this higher order stuff just disappears because what we're doing is actually exactly the Haskell evaluation. So we're really doing an interpretation of the abstract terms here that does exactly what Haskell would do. And in that way, we're avoiding the issues of lazy evaluation. We're avoiding the problems that you could have with normal higher order things like here this fix or like map or fold R or something. Yeah?
So if you do, for example, map, then you have to prove that the function that you pass in terminate. You can't do that.
Yeah, I mean that's
There's no modular.
there's a reason. There's a reason why we define start terms in the way we do. So we would say that you have map f l or something, and then f can be any terminating function. So for any terminating function, if we prove the termination of the start term map fl, then we know that map of this function to any list terminates. If it's not terminating, then of course it doesn't.
What it means is that now at every call site, you have to start analyzing, including the map. You cannot do a modular analysis where you
Right.
you have a contract for map that says it terminates if f is a terminating function.
Oh, it's not immediately clear how to do this. We have some work where we can do some kind of productivity analysis and some lazy termination analysis. And for some cases, there you can reuse this together with the information which arguments are strict. And then you get some kind of modularity. Yeah, no. Yeah, you're right. I mean, we have to do a whole program analysis. It's not possible to just do it intra-procedural or something. Yes. Yes. No, from is not terminating. I mean, if we do. Yeah, that would be terminating, and I would be pretty sure that we can do this.
Even though there's a call to map with a non-terminating function.
Yeah, that's like the take from. I mean, the take is called with a non-terminating function too. So that's not a problem because we're gonna go through this evaluation. And I think for this take map from, it should work.
So one reason why I'm asking is that usually I think people are interested to show that a certain function is terminating, not so much that the whole program is terminating. Because, for example,
Yes.
I'm a unification. I would be surprised if you could show that my unify function is terminating.
I don't think we could show that.
No, I don't.
I'm pretty sure.
You're very smart, so it could. So,
Yeah.
so I mean, any program that uses a unify procedure would never, you could never prove it terminates.
Yes, but we don't have to show the termination.
I just want to show smaller functions.
Right.
Would be nice to
But I mean, this kind of modularity we have. I mean, if the program contains like take and from, and I mean, maybe take depends on another function, whatever, then if you say, I want to know if take terminates, okay, you get this information, take terminates, if you give it terminating things. So if you use it in a way where you use from instead, then you have to say, oh, here I don't do take with terminating things, but I do take with something from something, and then I have to analyze this at this call site, yes. But I mean, so you can look at the program and see in which ways do I use take, and then you can do the analysis, and then you know that all places in the program where you use the take are fine. Or you can just verify the library.
non-terminating, but it would say take is terminating.
Yes.
As long as you give finite terminating arguments, and it may be terminating even when you give it a non-terminating argument.
Right.
But then you then I'll have
Well, then you have to analyze this special term, right?
Okay.
I mean, I don't see any way past this, actually. Okay. So we added Haskell here. And, what about the integers? I showed you that the things get much bigger. But how do we represent them? Well, we're not too clever right now. So for naturals, we just use the piano notation with 0 and successor. This is, of course, very bad if you have big constants. So we abstract constants above, I think, 800 or something, because it just blocks our memory. But otherwise, that's for naturals. That's pretty okay. But if you want to define integers, you need to do one of two things. Either you add some predecessor as another constructor, but then you're not free anymore. You have a non-free data structure because, 0 is the same as the predecessor of the successor of 0, and so on. And you have infinitely many representations for any integer. And you can get by this by doing some normalization rules. So there are people from, I think, Albuquerque who are doing these kind of things. And then if you add the rule P of S of X goes to X and S of P of X goes to X, then with some hard work, you might be able to prove something. But most of the techniques that we have, they don't do this. So what we did is we just take two constructors, pos and nec. And then we say, well, pos of 0 is 0, nec of 0 is also 0. Okay, we have to add always duplicates of for all the rules that we specify as axioms for the built-in operations. But for all the other integers, we have a unique representation. And this is maybe not optimal, but this works quite well in our proofs. And for what we are looking to extend this to is, of course, 32-bit vectors. Or 16-bit vectors or whatever size vectors. I think that should also work, but there showing things gets a bit more complicated because of the overflow, and many things that you would say are terminating with like mathematical integers, of course, are not. So we tested this thing on the Haskell libraries, on some of these libraries. So we took the whole prelude with 692 functions and, usual things like monad, maybe, list, finite map, queue. And we just, for each of the functions in there, we generated a start term. Then we looked at what we can analyze. And we, I think, gave it 5 minutes per functions. Most of them go in seconds, but some of them take quite a lot because there's a big hierarchy of functions, it's called. Or there are list comprehensions where you have concat map and these nasty things. Well, and in total, we could show termination of 994 of these 1,281 functions. And of course, of these 1,281, there's quite a number that don't terminate, like from is in the prelude. And Also, for all the things with I/O, we just safely assumed that maybe it doesn't terminate. I mean, if someone says, tells the user, give me some input, and the user never gives input, then does this terminate? Also, we don't have handling of floating point operations, so that also explains the gap that we still have here. But on most things, working on like lists and other data structures on monads, and it's pretty powerful. Yes?
The total is dependent on the star terms you gave it. So if you've given it different star terms, can that number actually go down?
Well, here we generated one star term for each of the functions. So always, if there's a function f in the module m, we would just say, okay, m.f with arbitrary terminating arguments. I mean, it depends on which kind of things you want to analyze. So it would probably be more useful to look at some implemented program and then show for all the used functions in those contexts that they are used with those arguments that they are terminating. We haven't done this yet, but we're looking into verifying the termination of another termination tool which is written in Haskell, but we don't have any hard results yet. But except for one nasty fixed point algorithm, it looks quite good. Okay. Well, future work would be that to take this termination graph approach and use it for Prolog to handle things like cuts and negation and built-in predicates. That's what we're currently doing. And then also to apply this to imperative programs. So for Java, we have major implementation done by a student, which is only working on like procedures, static procedures with integers. And that's taking this termination graph approach. Well, we feel that you could also handle things like recursive structures on the heap with this, but there's a lot of big challenges over there, so I'm going to go into that for the last minutes of my talk. So to conclude, what I have said so far is that there are two approaches to use these techniques that we have in our tool and that have been developed for decades in the term writing community. It's either do it directly on the domain and port this technique, the idea, and maybe reuse some search implementation, but mostly do a re-implementation, or just use a transformational approach. And this has been quite successful for both logic and functional programs. So also for functional programs, we're currently the only tool handling full Haskell 98. And on those subclasses where we can compare with other tools, we're way superior. Now we want to do this also for imperative programs, of course, because that's even more applied than logic programs and functional programs. But the representation here on the first side is a bit less natural. So in Haskell and in Prolog, we have terms that we work on. Our state is a term. And we have state transitions modifying the term. And so this maps quite nicely to term rewriting. But it's not that bad, because we can always describe the computation in the imperative program by a state transition too. And then if we have all those variables that are in scope, and we plug some function symbol around it, and then the arguments are just like the valuations before and afterwards, and we do this for all the blocks in our program, well, then this might work. And of course, generally the question is how to handle built-in structures. So for integers, I showed you what we do right now. So we have some term representation, but maybe this is not what you really want to do. Maybe you want to extend those existing term writing techniques, at least the ones that you use a lot, by knowing about integers. So they can reason about integers. They can call SAT modulo linear integer arithmetics or something to make more powerful proofs. And this is something another colleague of mine is just starting to get worked on. And well, then there's the question how to represent objects on the heap. That's where we came and thought, well, maybe let's take Boogie. Because the spec sharp to Boogie PL translation that already encodes the heap in an explicit formalism. And we would rather work on that one than trying to think of our own representation. And well, yeah, what you also could do is you could just say if you have a list with a next pointer, then well, the next pointer is the argument, and the class, let's call it node or something, is the constructor, and you have node of node of node of something as a list of 3 or 4 elements. But I'm not sure this will work on slightly more complicated things than lists. Well, and then there's the question how to handle object orientation, of course. I mean, virtual methods, what is being called, and pointer aliasing in general, and all these things. And so far we don't really know, but we hope that we can get some fruitful integration with work that has been done on the level of imperative programs. Well, what are the chances of doing this? Well, first, if you have some of your own data structures, not only integers, like, well, Byron's tool Terminator mostly works on integers, then we fear that representing them in some way by terms, or being able to reason about uninterpreted functions in general, would help to make the analysis more powerful. Then also, Terminator is not very good if you have in the condition of a loop some called some function of your own. And well, this function might compute minus, but it might also compute the successor or something. You don't know, and you have to analyze this. And this is something which in term writing you have to do all the time. And we are always making explicit all those built-in operations. So it doesn't matter for us if it's built-in or if the user has provided it. And well, then we don't assume an integer is an integer. I mean, if it's good for the proof, we are happy to interpret the successor function as minus 2 times x squared or something. It doesn't matter. So we have a lot more flexibility here. Well, then there are already existing techniques that go beyond just applying some ordering, some ranking function, but that have structural arguments that transform things by giving semantic annotations and things like that. And we wish to use these things also for the termination analysis of imperative programs. So what we would like to be able to do is add something like, I don't know, Java or C# or whatever down there as an input language. Well, yeah. And then be able to be successful on these programs too. So that's the end. Well, one more thing, of course. I mean, I've got an apple here, so let's do the Steve note. And here, let's say we have Boogie as a set. Some tool, external, internal, generates BoogiePL. And then let's say we have a nice translation of all the constructs. Well, there are not so many in BoogiePL. And we then transform this into either a term writing or directly to the level of dependency pairs, which is probably more wise to do. Well, then we would be able to analyze like C# programs or even spec# programs where you also have some annotations that are probably also helpful in showing termination. And there's translations from annotated Java functions. There's from C, verified C, and we would gain a lot of things. And if people generate new BoogiePL front ends, then we would be happy to also try our tool on these programs. Well, this way we would get like a Boogie-based front end, and then we have our modular techniques on the back end. Or if we like Pink more, I mean, then there's always Clouseau. Well, we've already in this week developed an interface called Benini. And well, it's, you know the son of the Pink Panther? It was the idea of Francesco. Anyway, not very surprising, no, I guess. Well, in this way, we can take those things that Clouseau works on. I mean, everything you can compile to a Microsoft Intermediate language, basically. And then we generate by Clouseau the control flow graph. And for all the blocks, we have like some invariants which we additionally can infer and analyze. And then this state transitions together with the conditions we encode into basically a term writing system, or let's say also into a dependency pair problem. And this is then fed in our system, and we show termination of this. And in this way, we get a nice pipeline, an alternative to BoogiePL. This is going to take care of all those pointer aliasing things and accessing fields. It's probably at the moment not going to be very powerful on recursive data structures, but that's a good start, I would say. And well, let's look at a small example. So this is a C# method where, well, we look if x is smaller than 0, it's 0. And otherwise, we do repeated subtraction until x is smaller than y. And we have then in z our quotient of x and y. And so this is probably not terminating without this contract, because if you repeatedly subtract 0, you can do this a lot of times, and the condition of the loop will still hold. But if we have this requires up here, then, well, this will be in the Benini annotations, and we will be able to put this as a condition in the loop here. And, well, this part of transferring the invariance is not fully automated yet, but everything else Francesco and I have been able to do. Oh, this is the wrong one. Where is it? There we are. So that's what the input looks like. So there's a lot of state. A lot of this state is not relevant to the question we're looking at. But here I added always this y is greater than 0 conditions to the loop. So I did this part manually. The rest is the output of Francesco's new output interface. And now if we analyze this, it will first give me a graph here, and we see the state space is pretty big for each of the states, but only the recursion, only this loop here is important to analyze. And here the liveness analysis says, okay, these two variables are the only ones interesting, and it tracks what they get assigned to in this loop. Well, and if I now close this analysis, then the termination proof starts. And then we get a proof. And of course, for this proof, it directly goes here to dependency pairs and then applies a number of simplification steps. And in the end, I think it uses, not surprisingly, some ordering, which, where is it? I don't find it on this small screen right now, but it uses an ordering where it approximates minus by just the first argument. And because it does some case analysis before for the other cases, it makes sure that this thing is really terminating. Yes, so what we add is this post-neck and piano notation. You can see it directly at the first problem being generated. Maybe. Yeah, it's here. Okay, so yeah, that's all those axioms that we have to add. So here, axioms for greater, axioms for subtraction. Subtraction is based then, depending on if we have negative or positive arguments, on either natural addition or natural subtraction. Then we have less than, and we have and we don't have any not in this example. So now this is really the end, and I'm happy to take questions, more questions. Mm-hmm. Okay, I haven't tried the Hanoi function yet. In general, it's not a problem to switch the parameters. So I mean, the size change principle, for example, that goes and we have this in two variants in our tool, that goes and looks at how do the parameters change. So it can say, oh, this one goes down there and this one goes up here, and then it looks at if I can generate the transitive closure of this, what I have there. Yes. I mean, you have to approximate that, but that's what the size change principle does. So that would be one technique which can do this. And depending on how exactly the encoded TRS looks, there will be other techniques which will also be able to handle this swapping of arguments. I'm not sure about the Hanoi function because I honestly haven't tried it. I would guess so. Sure. Yes?
I was sort of expecting now that we have all these front-end languages that we would have a take on sort of the direct approach. Suppose that faculty or students in Illinois would translate programming language to give operational semantics to Haskell and Prolog in Mall. Okay, so I would take your Haskell program,
Mm-hmm.
get your operational semantics of Haskell and partially whatever it is with respect to the operational semantics, and I would check sort of termination of that rewriting system. Why is that a bad approach?
Well, I don't know if it's a bad approach, but I would guess that this whole operational semantics would probably be quite big, and I don't know if it would be nasty or not. That's I haven't tried it.
Itself is big, but then you specialize your program with respect to semantics and then terminate system.
I mean, this is somehow like the closed thing we're doing. There we are like we have these operations like less than and subtraction, whatever, and we have all these axioms somewhere that tell how these work, and then we of course slice it down to those that we need. But I mean, that's I'm not sure. So how would it exactly work? You have this axiomatization of the operational semantics, and then and then you give the program as or what kind of?
Then you have a program.
Yes.
Now the execution of that program is a special instance of that operational semantics. So you specialize the semantic with respect to the program. Does that correspond to what you're doing in the translation approach?
Yeah, I think in a way it does. I mean, we're just like in model checking, you can do an explicit enumeration of the state space and then model check on that, or you can just build that part that you just need for the analysis. At the moment, we are more like taking the operational semantics, or we haven't specified them as term rewriting or something, but just in Java routines that work on well, our abstract start terms, and then in a way we specialize these things, but it's a bit different, and I'm not sure what would happen if one would take this approach.
Then you could think of the operational semantics as a term rewriting system, one of whose inputs is a term representing the program.
Yeah, okay, but then you would.
If you did that, then all you have to prove is the termination of that.
And that would be a large term rewriting system. So you specialize it.
So it would basically be.
Is there still an advantage of using things? You're doing it sort of directly from Haskell,
Mm-hmm.
as opposed to putting over this.
I mean, I imagine that if you take this approach of giving the program as a term and basically having an interpreter and then specializing this, you would need a very good program specializer. And I mean, I'm not sure about, yeah. Yes. Yes, but I mean the the interpreter is kind of hard to analyze, probably.
But your termination graph state is a bit like the specializer.
Yes.
Unfolds the various executions of the program.
Sure. I mean, these termination graphs that we built, they are very closely related to those things that people in partial evaluation and program specialization do. So actually, for logic programming, we are also looking at those things they did with Ecke and other tools. And the difference is more that we are not interested in operational equality. I mean, it doesn't have to do the same thing. I mean, we're very happy if it preserves non-termination, because then it's sound. And if it preserves termination, even better, then we can also prove non-termination. But it doesn't have to do the same thing. So it can alter the semantics almost arbitrarily. And in fact, we're only looking at a small part of the semantics. I mean, for the C# program, we just have to look at the loop. And we're not interested in what this procedure computes. Of course, this changes once...
Termination might depend on that.
it might depend if this procedure is called from somewhere else. So that's the thing that where with Clouseau it will be a bit difficult, because Clouseau is an interprocedural analysis, and well, if you call some other procedure, then you can't really approximate very fine what this procedure is going to have an effect on the state space. So. But we haven't tried this yet.